Alright, gentle people, let's get started with section 15.x. Alright, all jokes aside, guys, this is obviously not an official section. I just thought I would provide a quick, derivation of the integrated rate law for higher orders than n equals 2. I thought that'd be a fun exercise to do to solidify understanding in not only calculus but also the rate law itself. So if you're interested in perhaps a more rigorous approach to proving what the integrated rate law is for a generic order n reaction, this video is for you. So let's get started. I have some notes here on the side that I've worked out, and we're just going to go through it. And hopefully by the end of this you'll have a decent understanding of the calculus behind it and how we arrived at our answer. So the first fundamental axiom that we're going to start at is what was presented in Christo's lecture. So and that is the axiom that you can take the rate, or actually you can take the negative rate. So negative, let me adjust my pen size here, that's a little too thick. You can take the negative rate, so dA dt, and set that equal to k times a to the n, right? So here, this was written in the lecture as the rate, and this is the differential rate law because it's a differential equation, is equal to a to some power n, right? And here we're just looking at the general reaction, a goes to b, as was done in lecture. And we have this negative sign here because, as Chris just said, generally the rate is written as positive, and a here is going to be decreasing over time. So this is really the only fundamental axiom that we're going to start with, is that we can write the rate law in its differential form, and we're going to use some calculus to bring it into its general integrated form without ever plugging in a number here for n. So let's go ahead and do that. This differential equation here is separable. So the first thing I'm going to do is I'm going to multiply dt on both sides. So I'm going to multiply dt on this side and dt on this side. Notice here on the left we get negative dA is equal to k a to the n dt. Okay? Now what I'm really trying to do here is I'm trying to separate the variables, right? So I'm going to try and get all the t's and dt's on one side, and I'm going to try and get all the concentrations and the differential of the concentrations on one side. So there are no t's, so I can keep this dt here. However, these two are on different sides of the equation. That's not good. The differential of a and the a itself are on different sides. So I'm going to go ahead and divide both sides by a to the n. So I'm going to multiply by 1 over a to the n. Do that on this side as well. And what you'll notice here is on the left side that simplifies to 1 over a to the n. I'm going to bring the negative sign out front, dA. And on this side, the equals k. This cancels with this, so we just get k dt. Great. So now we've taken the general way that we write the differential rate law, and we've separated the variables. So now we're ready for integration. Now in integration, it's very important to define your bounds of integration. So we're going to be very careful with how we do that here today. Let's start by integrating both sides. I'm going to keep this negative sign outside of the integral because it's equivalent to just saying -1 times this, and you can move multiplicative constants outside of integral signs. So I'm just going to keep the -1 outside the integral for right now, and I'm going to take the integral on both sides. Actually, let me do that on a new line because, as I mentioned before, it's very important to look at your bounds of integration. So we're going to be very careful with how we do that. All right, because these are not going to be indefinite integrals. These are going to be definite integrals. So on this side here, notice the differential that we're integrating with respect to is dt. So on the right side, we're essentially adding up all the time that's gone by. So we want to integrate here from time t equals 0 to t equals some final time. I'll denote that t sub f. It's important to note that it is technically incorrect to write this integral from 0 to t because you're using t here 2 times. And this t is a constant, and this is a differential, and if you've taken a calculus class, you've probably been told that doesn't make sense. And if I was teaching calculus right now, I would go into why that doesn't make sense. But I'm not teaching calculus. I am merely trying to provide a proof. So instead of using t up here, we're going to use t sub f. So we're gonna explicitly say t equals 0 to t equals t sub f, some final time. All right. On the left side here, we're going to integrate this. And what are we integrating from? Well, I'm going to integrate from A. The concentration of A is equal to some A final. And then, oh, sorry, let's let's start integrating from A initial. We'll call that A naught. And then integrate to A is equal to A final. There we go. So those are our bounds of integration that we're going to do. Now, if you look at these two integrals, the right side is much easier to do. So let's go ahead and get the right side done. So I'm going to take this integral right here and just do the right side in front of you right now. It's very easy. So here, the integral from t equals 0 to t equals tf. Well, we first have to ask ourselves, is k a function of t? We're integrating with respect to t, right? And we know that k is k may be a function of capital T, temperature, right? We've learned that. But lowercase t, in this case time, it is not a function of time, right? This constant stays the same for all time. So therefore, we can pull it out front. And then here, we just get the equivalent of 1 times dt. So we're integrating with respect to dt. And what are we integrating? We're integrating 1. All right. So therefore, the integral is equal to just t, kt, evaluated at t equals 0 and t equals tf, which is equal to ktf minus k times 0, which is equal to ktf. Don't know why that f went right there. ktf. Good. So this is the right-hand side of the integral evaluated. And this is the same thing that Chris Joe did in his lecture. But now we're going to evaluate this left side with this arbitrary n. We're not going to plug in the order of the reaction, right? So we're going to try and do an arbitrary n here. And to do that, we're going to make use of the inverse power rule. So let's go ahead and just quickly review how that goes. So the inverse power rule, let's just quickly review that from our integral calculus. So if we have an integral of x to the, let's do capital N, so we don't mix up variables, we know that this is equal to x to the capital N plus 1. We increment n, and then we divide by the new exponent, n plus 1. And this is an indefinite integral, so remember to add your plus c. Okay, so I'm just going to say right now that this is only going to work for cases where n is not equal to 1. And I actually haven't checked the 0 case. So just to be safe, I'm going to say that I'm proving this for when n, the eraser, for when n is greater than 1, right? And why do I say that? Let's look at the case where little n is equal to 1 and see what happens when we try to apply the inverse power rule. So if we have little n is greater than 1, then we have this integral, and this is from a naught. Actually, let's write this in proper form. A concentration naught to a concentration final of 1 over a dA. Remember, we had a negative sign out here. If I try and use this, let's plug in n equals 1 to here. So if I do n equals 1, well, how can I write this? This is equivalent as saying negative, do our bounds of integration, always, All right, so if I plug in, so remember, 1 over a is the same thing as saying a to the negative 1, right? So essentially here, what we're doing is we're integrating a to the negative 1 dA. Okay, so if I plug in n equals 1, that just is a 1 exponent there, right? Remember, we had our n here, and if I plug it in, then it's just equal to this, which is equal to this. And let's look at what happens when we try to apply the inverse power rule here. When we try to apply that, we're going to get that this is equal to negative the integral a naught to a final of a, in this case our n is 1, our big N is equal to our little n, and that's 1, plus, sorry, no, they're not equal. Here, this n corresponds to this big N, and it's negative 1. And so we're going to add 1 to that. So that's going to be a to the 0th power over, and then if you look on the denominator, here we're going to take the n, which was negative 1, and we're going to add 1 to it, which is 0. So if we integrate this, we divide by 0, and that's not good. So that's why the result of a first order reaction, the integrated rate law for a first order reaction involves a natural log, because if you try and use the inverse power rule, you're going to divide by 0, and that's not good. So with that caveat out of the way, let's go ahead and go back to deriving our integrated rate law for cases where n is greater than 1 using the inverse power rule. So let's go ahead and look at this. So I'm just going to write down here, very important, only works for rates of order 2 or larger. N is greater than 1. Okay, so let's go back to actually deriving the integrated rate law for a general n. Now that we have this caveat out of the way, and we know the stipulation that we have, we know that this is what we're looking at, and this is what we must have satisfied in order for our solution to hold any weight. And it's very important when you're doing math like this to look at when you could be dividing by 0 or taking the root of a negative number or doing something a bit icky, especially when you're in a physical science like this. And it's very important to look at that and to keep your assumptions and keep them at the forefront of your mind, or at least write them down and box them. So here I'm boxing that this solution that we're going to come to will give us the integrated rate law for any order n as long as the order is greater than 1. So that's something very important I want to point out. All right, so if we continue working, we recall that we already evaluated the right side, and we said that the right side was equal to kt final when we integrated it. And now we're working on evaluating the integral of the left side. We're working on evaluating this integral right here. So I'm going to go ahead and rewrite that, and we're going to use the inverse power rule to evaluate that. So here, let's move this up a little bit. Okay. So here, the integral we're trying to evaluate is negative the integral from a naught to a final of 1 over a to the n dA. That's the integral we're trying to evaluate here, where n is some arbitrary constant greater than 1. And what we're going to do is we're going to use the inverse power rule here. So to do this, what we're going to do is we're going to say, okay, we can actually rewrite this. This is equal to negative same bounds of integration, except it's 1 over this, and we know that when we have an exponent in the denominator, that's equivalent to just writing the same thing but with the same exponent and a negative sign out front, so negative n dA. Okay, so now we have it in the same form that I showed up here. So this allows us to set this negative n equal to capital N and then apply the inverse power rule. So remember, I'm set capital N and lowercase n are different. Lowercase n is the rate of our order of our reaction with respect to A, and capital N there is just denoting how to use the inverse power rule when you have capital N in this form here. So here I'm going to set capital N equal to negative lowercase m, and we're going to apply the inverse power rule. So when we apply the inverse power rule here, what we're going to get is we're going to keep the negative sign out front, and we are going to get the concentration of A to the negative n plus 1 over negative n plus 1. And because, if this was a indefinite integral, we could just add c here and we'd be done, but we do have bounds of integration to worry about. So this is going to be evaluated at A is equal to A naught, the initial concentration, and A is equal to A final, the final concentration at some time, T final. Okay, Reddit says I have been working on a kinematic airplane. Cool. All right. Not very likely. All right. Can I mute these? Can I mute settings? Yeah, turn them off. All right. Back to work. All right. So we've integrated this successfully with the stipulation that n is greater than 1. Now let's go ahead and apply our bounds to the integrand. So here we go. So this is going to be equal to, I'm going to pull the negative sign out front of the whole thing, and I'm going to say it's equal to A final negative n plus 1 over negative n plus 1, okay, minus A naught negative n plus 1 over negative n plus 1. Good. Notice this negative sign here has the effect of making this a negative and making this a positive. It's just going to flip what they are, so I'm going to rewrite them in the opposite order. So I'm going to say that is equal to A naught negative n plus 1 over negative n plus 1 minus A final negative n plus 1 over negative n plus 1. What can I factor out of this expression? Well, it's clearly a 1 over negative n plus 1. So I'm going to rewrite this as 1 over negative n plus 1 times A times A naught negative n plus 1 minus A final negative n plus 1. And let's go ahead and clean up the work a little bit here. My mistake, the naught should be outside here. All right. Looking good. So this is the right side of our equation, right? This is the right side. Well, it's the right or the left side, depending on how you look at it. So remember, we were integrating both sides. We integrated the side with respect to t, and we got this answer here. And now we're integrating this side, so I guess it would be the left side with how I wrote it. So we can set this equal to kt final. So I'm going to set this equal to kt final. Equal to kt final. Okay, good. Now, really, when we're doing these problems, it's often useful to solve for the final concentration, right? Because that's what the integrated rate law is generally going to give you at the end of the day, right? You're going to take some initial concentration, the order of the reaction, some constant K, some time that goes by, and you want to figure out what's the final concentration, how much do you have left or do you have accumulated? So really what's going to be useful for us here is to solve for this final concentration term. And to do that, I'm going to go ahead and multiply both sides by negative n plus 1, by the quantity negative n plus 1. So if I do that, I go ahead and get rid of that here, and then I have negative n plus 1 over here. Okay? So I'll go ahead and write this again. We have a naught negative n plus 1. And my buddy Aaron says, how's it going? I will let him know after I'm done with this. Negative n plus 1, good, is equal to kt final and negative n plus 1. Okay, cool. So this is the general integrated rate law, but we still have some work that we could do. For example, if we wanted to isolate this final, we could go ahead and move the initial concentration over to the other side pretty easily. So let's go ahead and do that. I'll subtract it from both sides. That gives us negative a final, negative n plus 1 is equal to kt final, negative n plus 1, minus, so I'm subtracting from both sides, a naught, negative n plus 1. Good. Now here we have a negative sign out here. Remember I said usually we're solving for the final concentration, so it would be good to multiply both sides by negative 1 and get rid of that negative sign. So I'm going to write this as a final, negative n plus 1 is equal to, and I always like writing positive things first, just a preference of mine, and probably a preference of most of yours. It looks a bit ugly if you don't. So you can confirm that this does in fact equal this. And there I am breaking my own rule here. I just said that it was more pretty to write positive things first, and you notice that this n is written first. So in fact, what I'm going to do is I'm going to say that this is the same as 1 minus n, which it is. Positive 1 and a negative n. Good? All right. So now we're a bit cleaned up, and you could leave it here. You could say this is your general rate law for a reaction of order n with respect to A as long as n is greater than 1. You could leave it here. You could simplify a little bit. You could do that. What I'm going to quickly do is I'm going to quickly show you that this does in fact work. So let's go ahead and do that with setting n equal to 2. So if we set, let's let n equal to 2. So this is a second order reaction. This is one that we are studying in this class. And this is something we can plug in. So let's go ahead and do that. So let's plug that into our expression here. I'll go ahead and box this. Ooh, that was a horrible box. Let's get a nice blue color, something to make it stand out a bit. So we're going to go ahead and box this. This is our general rate law for an order n. And let's make sure that we are aware that n is greater than 1 for this to work. And in fact, 2 is greater than 1. You can take my word for that. Otherwise, look it up. Okay. So let's go ahead and plug in 2 for this. So we get a final. Negative 2 plus 1 is equal to a initial negative 2 plus 1 minus k t final 1, and we're subtracting 2. Minus 2. Okay, so what do we get here? Well, negative 2 plus 1 is negative 1. So this is going to be a final to the negative 1 power, which is the same as 1 over a final, which is equal to, same argument for this term, 1 over a initial. And then here, 1 minus 2 is negative 1. So it's not going to change the magnitude of this term, but it is going to change the sign, right? We're multiplying by a 1. How many 1s are there? There's a negative 1. There's a positive 1. Which one are we multiplying by? We're multiplying by the negative 1, so it's going to change the sign here to a positive. Plus kt final. And this is for n equals 2. You can confirm in the book this is in fact the integrated rate law for when n equals 2. And this general expression that I've derived will work for any rate 2 or greater. I haven't explored fractional rates, like let's say 3/2. That is in fact greater than 1. Could you have a rate with a rate of 3/2? I'm not sure. That's a question for our professor. I am no master in chemistry. but this is something that at least I can derive for you today. And perhaps this was interesting for some of you. Real quick, what I want to do is do one more simplification step. Technically, what we could do is if we really wanted to solve for a final, notice how we have this negative n plus 1 in the exponent there on a final. We could take the root on both sides, and that would perhaps be more simplified. So let's go ahead and do that actually. So we're going to use this, and we're just going to simplify a little bit. So here we'll take the root of negative n plus 1. Now, when you take a square root and you have a negative number right here, it kind of throws your brain off a little bit. So what I'm going to do is, we know that the square root of, let's use alpha, is really equal to x to the 1 over alpha. I'm just going to use this notation here instead of the square root notation, because when you have a negative in the exponent, your brain can kind of make sense of it. That's usually when we talk about negatives and exponents. But when you have a negative as the root, it kind of I don't know, kind of screws with you. It screws with me at least. So I'm going to be using the exponent notation for square roots. So here, that is equal to this whole quantity, a naught to the negative n plus 1 minus ktf 1 minus n. This whole quantity raised to the 1 over negative n plus 1. That's the same thing as taking the negative n plus 1 root of it. All right, so we have this. Now, this expression here is fine how it is. Let me just take a look at my notes here. Yeah, this expression here is fine how it is. This may be another way you want to write the integrated rate law, because this is really solving for a final explicitly. Here, this one here, we're solving for a final, but we do have it raised to this power. So both of these expressions should check out for a rate n greater than 1. I know I'm beating a bush here, but this is very important, this stipulation, because if n is equal to 1, you need to use a natural log, otherwise you divide by 0. So, all right, so hopefully this was interesting to some of you, deriving the general integrated rate law for reaction order n. And for others, it probably wasn't that interesting. But if it wasn't interesting, you wouldn't be listening to me right now. You would have clicked off a long time ago. So thanks again for listening, gentle people, and stay safe. Chem 1C.